Yeah, I'm sort of wondering. Oh, actually, so. What was that? Sounds good. Good. This is just, I guess, like, why sounds good. But I think it's just make the features. Yeah. Sorry, I think earlier over at work. I can submit it once we get back. I can submit it really. Okay. Yeah. Okay. I think we should start collecting more clips or images of people we want to. Well, you can probably find a clip that we want to see. Oh, you did? We can't find college Facebook. Right with the script of take that we frame. Yeah, no, I oh yeah, that's nice. Is that the celebrity?
You had to that's collaboration.
Yeah.
That is, I don't know. Like, did you have to write the whole provisions of
All right, let's get started. How's everybody doing?
Great.
Good? Good. You're doing well on project proposals? Up there? A lot of you have set questions and things, that's great. Hopefully you get the answers you need and you'll have something turned in by tomorrow. Any questions on this before we get started? Okay. How's the new homework? Have you started with the new homework yet? Yeah. Okay. So you made a comment that you like hands. It's kind of fun, huh?
I have a question about the homework report. I have posted it on discussion.
Got it.
What was the question?
So are you saying go look at the discussion? I'll take it. Duly noted. All right. So let's continue with neural machine translation. So we got going. Oh yeah. This is too hard for me. Okay, so we did part one, and we got some of the basics. Yeah.
It sounds like the audio is not working on the live stream.
Oh, okay. Don't know.
I don't know either.
Oh, never mind. Sorry, they were mistaken.
Okay. Thank you, though. Thanks for watching out for everyone. All right. So we got started. We learned a little bit about, like the first really good attempts of doing this with like end-to-end training. We learned about the model seek-to-seek, so sequence to sequence. It was pretty awesome, but it has some issues that we talked about, and today we're gonna go through some of the solutions that were put in place to kind of overcome those. and kind of look to the next set of lectures on like the most modern uses of neural networks for doing machine translation. But remember, we ended on this. This is just to kind of remind you that even our best attempts sometimes go bad. Okay, so what are some of the limitations? Well, there are three main ones that we're going to talk about today and methods for overcoming them. So one is just the vocabulary size problem. So if you, like in its basic formulation, you, at each like step in the sequence, you're trying to, make a decision amongst, for a symbol or a word, amongst all the words or symbols in your vocabulary. And for actual language, this is large. This could be huge. And not only that, like it's a problem because many words. So there are a lot of words that are super common, and then there are many words that rarely occur. And so you have this kind of imbalanced distribution on the vocabulary for how often they appear, and so this could be a challenge. We're going to talk about how to overcome that, or some approaches for overcoming that within the seek-to-seek framework. Sentence length. So we talked a lot about this at the end of last time. So machine translation, especially using seek-to-seek, has a real hard time translating long sentences because it starts. So even though we might use like LSTMs, which kind of help with the vanishing gradient problem, they're still very difficult to learn long distance relationships, to have a long distance relationship between the words at the beginning and end of sentences. It's just a fact about how these things are set up. I didn't put this out last time, but it is an interesting fact that in the original seek-to-seek paper, they actually input the source sentence backwards. Yeah, they put it in backwards, and so that seemed to help a little bit in the translation. It sort of put so between the two sequences, it put the ends of the sentences right next to each other, but it made put the beginnings of the sentences like really far apart. But they sort of found that helped, and it has something to do with this length problem, although that was quickly overcome. And then the third problem here is language complexity. So, like we mentioned a bunch of times, it just turns out with language, there's a lot of ways to say the same thing. There are these kind of unusual words that show up that need to be translated, but you may not have seen it many times in the training data. And languages can be complex, like the grammars can be complex between different languages, like a Romantic language and Arabic language, like that, have really different like statistical structures, and so this can just be difficult. So we'll look at some of the ways that that we proposed to overcome this. All right, so this is our plan for today. Proposed solutions. So we're going to talk about copy mechanism, the attention mechanism. This is going to be really important, and then character level translation when things are very complex. All right, so so this is just talking about the vocabulary problem a bit. So we've gone through a great part of the semester talking a lot about ImageNet and how all this progress on ImageNet, and like that data set for the years in which it was really used to benchmark progress in computer vision. There was still just a prediction on 1,000 categories, right? So that's a lot, but it's still only 1,000 and pretty manageable. When you go to language, you really just you can sort of restrict your images to only have to be from like 1,000 different objects. Like that's not a big deal, but you can't just like go to language and then just restrict it to have like 1,000 words, right? Like all of a sudden you can't make hardly any sentences. It doesn't make any sense. Like you can't just kind of artificially constrain the vocabulary. So you have to deal with this like right away. So these vocabularies again can just be really, really large. So how do you, in this case, how do you choose the word mat amongst possibly millions of words in your vocabulary. So, yeah, this is something known as like the word generation problem. So, if you have a modest sized vocabulary, you can just do what we talked about last time, like in this kind of simple setup, where you just you just have a softmax. So the output from any one of these decoder units is just it's a softmax output over the vocabulary, and then you just do maximum life max. You just choose the word that has the largest probability assigned to it. You really hope that it's like peaked around that word, so it's really confident about it. But whatever, this is what you do. You pick the next word, and you hope you get it right or close to being right. And so this is suggesting, from a couple years ago, like 50,000, like a vocabulary of 50,000 would be, kind of like that would tend to work on GPUs from a couple of years ago. And so, you could do a lot with that. However, this can become quite a tricky problem still, even with a small vocabulary, if again you have words that that don't appear very often. So this is kind of showing an example of this. So anybody from France or been to France and know about the ecotax? This was like, anyways, around the time a lot of these papers were being published, it was like a big deal in the news. So this was an example you see a bunch of. But anyways, these are like ways of taxing people for using roads. Anyways, the point is that you have like weird words like ecotax, and maybe like place words here, proper nouns like this point de bois or bouillie or however that's said, and like these are really difficult words to translate because like one, they're new to the language in some sense, and they don't happen that often. So one way to sort of like deal with this without doing a whole lot is just to say like, look, I have a vocabulary of size 50,000. It'll have words in it like the and portico and in, but it's not going to have words in it like all my proper names and places, and then like just kind of strange, unique words like this. And so when you go to do translation, you can sort of pre-process and just say like, look, there's a word that goes here. It's not in our vocabulary, but I'm just going to mark its place here. So kind of like there's like a stop symbol for like when we have to stop a sentence when we're doing the seek-to-seek model, the encoder and decoder. We now kind of introduce a new symbol to the vocabulary that's like, hey, there's an unknown word here, something that's not in our vocabulary, and so we can, and so what you have now. So this was the original pair of words that you needed to translate one to the other. So now you do this pre-processing, and now you need to translate this one to the other. So you kind of, you think about it like it's still a translation problem, just sort of a weird one because, what you're trying to learn to do is like, when you do the translation is put this unknown to this unknown and vice versa. And this unknown somehow needed to be expanded into two unknowns and collapse into one unknown, going back the other direction. So this is a way to kind of start thinking about this, like how do you deal with this? And you could do this, and you get translations that have these unknown symbols in them, and you might think you could stop there, but yeah.
Why do we just only select those words to have unknown?
Because we're just assuming that like we have a fixed vocabulary, and those words didn't show up in our vocabulary, right? So like that point de bois or however you say it, it's a place. It's a place, or like that's actually probably like a bridge or something, and so this is not going to appear in our vocabulary. Like we're not going to put every single proper name ever in our vocabulary. We're just going to say like, hey, if it's a proper name, we're not going to try to translate it. And then the other one was just, it's kind of a weird word that doesn't appear in any vocabulary except for when you're talking about, taxing roads in France. And so it's so unique that we're just going, it's not going to be in a vocabulary as well. So the way we kind of show that it's not our vocabulary is that we replace it with some symbol that just says like, hey, there's a word here, but it's not our vocabulary. So deal with it. Deal with it, machine learning. However, there's actually a pretty simple kind of way to deal with this if you think about it. Maybe you already saw it and you're just waiting for me to just get through with this because it seems so obvious. But it's the fact that when you do have these unknowns, remember that you still have the like in the source sentence, you still know what that word is. So just bring that word along down to where the corresponding unknown symbol shows up in the translated sentence, and just put it there. And if you do that most of the time, you're gonna be good, because again, the words that don't appear in your vocabulary being unique, they tend that tends to be like a very valid way of dealing with it. So let's look at this. So here's how this works. So you not only want to learn to do the translation that includes these unknown symbols, you want to learn to do alignments as well. So what that means, what alignments means is that each of your unknown symbols in your translation has some sort of index associated with it, suggesting that something about the original location in the source sentence. So that just carries, so now what you're doing when you're learning this is not just to put the unknown symbol there, but to put some sort of relative relationship about where it appeared in the original sentence. And you want to learn this. So this is like additional annotations in your training data. So that when you learn to do the translations, you not only put the unknowns in, but you put something about the relative positions in as well. So you're predicting the unknown and these relative positions. And then once you have that, then you can do this sort of copying mechanism. So so it looks something like the following. Yeah, so once you've done that in post-processing, you go, okay, I have this unknown symbol. It corresponds to this unknown symbol. I don't know what to do with that. I'm just going to go ahead and copy that word down to here and hope for the best. And then same thing over here. I have this unknown symbol. It corresponds to this unknown symbol. And so I don't know what that is, but I'm just going to copy it down over here. And in general, that's going to work fairly well. And so you might have wondered, for instance, on this, remember this didn't show up in the French vocabulary. So how do we put the right French word here? And so what you just do is you use a dictionary. So somebody's already got, in this case, an English to French dictionary, English-French dictionary. So you just do a lookup. You say, okay, as I copy, let's go see if that word exists in the dictionary. If it doesn't, I'll just copy it straight across. If it doesn't, if it doesn't exist in the dictionary, I'll just copy it straight down. If it does, I'll just look up its translation in that dictionary and put it there. So it's some sort of like post-processing after the fact. And this actually gets you a long ways. So you learn. So you get a translated sentence. It's grammatically correct because you learn the kind of you learn the grammatical kind of positioning as part of the translation. And then for these words that were really rare in the vocabulary, you just do this little trick. And, after the prediction, And this really, really, really improves your ability to do prediction. So yeah. So questions about that? Does it seem kind of like a cheat to grab a dictionary and do this? I mean, it's not a cheat in the following sense. What we're trying to do is like translation like sentences to sentences, right? Which is very different from translating words to words. Because the sentences require us to get the grammar right and the translation of the grammar between the two sentences. So it's like we're trying to do more than this, so it's like okay that we kind of cheat and grab a dictionary for this. And it's cheating in the sense of of like being like fully end to end. It's not fully end to end anymore. But dictionaries exist like this. What doesn't exist is like sentence to sentence dictionaries, right? So machine learning is doing the heavy lifting of the sentence to sentence translations, and then we just pick up the dictionary to do some of the rare word translations. Does that make sense?
Okay.
Yeah.
So is the dictionary just the parameters we need to record? Or
The dictionary.
the dictionary is it the parameter or we don't?
Yeah, it's like you could think of it as a parameter, but it's just like it's just a lookup table that you've got available to yourself, and you just query with echotax and come up with echotaxe or whatever. It's outside of the machine learning for sure. So this is no longer end to end, but it's your computer can do this in small fraction of a second. So this hardly adds any time to the full like end to end translation process, right? Simple lookup.
And also the correspondence is like a label, right?
Yeah, so that has to be learned. Yeah, so again, like you add those annotations. So when you do add the unknown label, you also add the fact that this unknown kind of switched to this unknown, and yeah, like so that becomes a prediction of the model now. So just an additional label that just has to be predicted. Not that big of a deal, but it just has to be done. So you're adding basically think of it as like adding just a couple of words to the vocabulary. All right, making sense? I mean, enough, like, it doesn't have to make sense, like, you can go out and code this tomorrow, but it makes sense, like, how people approach this problem. I think it's pretty clever. I actually like this a lot. Sometimes, like, when you do machine learning, you want everything to be so end-to-end, like, you forget that, like, there's some really easy ways to, like, deal with some problems. And this is, like, a really easy way to deal with this problem. You might, like, spend so much time trying to do, like, how do I like, work with vocabularies that are, have millions of symbols. You could try to figure that out. There's probably some great way of doing that. But this is like a super, much easier way of doing it and works really well. Okay. Okay, so what happens when you do this? So, so let's see. This was from like our state-of-the-art statistical machine translation system, the SMT system. This is from the just seek to seek, and this is seek to seek plus this copy mechanism. And then what this is showing you is this blue score for sentences that kind of like ordered by like more frequent to less frequent. Okay, some way of specifying that, and you can see like for sentences that appear more frequently or have words in them that appear more frequently, you can see that the blue score from both the seek to seek and seek to seek plus copy are doing better than the SMT state of the art, and that is true for both of those up until about about 1200 rank 1200, and then this. So for these more rare sentences, the seek to seek starts to really fall apart, but the seek to seek plus copy does about the same as the state of the art in SMT. So what's cool about this is that according to this measure, this is your first neural machine translation that is state of the art compared to anything else out there. The best being these statistical machine translation systems. So that's cool. So just adding that one additional mechanism, this copy mechanism, gets this to be state of the art. So now all of a sudden, neural networks are winning. We like that.
Yeah, right.
We like that. And yeah, although it should be admitted that like as soon as you add the copy mechanism, this starts to have a little starts to look a little bit more like a statistical machine translation system in the sense that like it's cobbling together a couple different pieces of things. It's not fully end to end, but it's also not as onerous or as complicated as any statistical machine translation, like this one in particular. Okay, cool. We good? Yeah, so here's some additional examples of this for maybe sentences that are more interesting to look at. So what you have in these, we're going to see a couple of these as we go through the lecture. We have our original source sentence is in English. Then we have a human translation of that. So again, there's probably many ways to translate this, but this is like one of the most faithful. And then here is here's translation with the unknown symbols still in them with their orderings. And then you have the translation plus this copy mechanism. So it turns out that cataract doesn't appear in the vocabulary that they used when doing the machine translation. That kind of makes sense. That seems like a pretty rare word. You only talk about it when usually talking about eyes, which is what this is. So pretty rare. So this needed to be copied down. Also interesting, the number 2600. Of course, like trying to put every single number in your vocabulary would expand its size to a pretty large size, maybe infinite, I guess. So that ends up being an unknown too. And so copy mechanism for numbers, and then dictionary lookup for cataract, and this is what you get. So it's not the exact same sentence, obviously, but where was our French reader from last time? He's not here. This I believe this is grammatically correct, so that's good, and carries the same the same meaning. And so like the blue score here, is taking like this source or this translated sentence, this human translated sentence as like ground truth, and then this machine translated sentence, and it starts to do comparisons of like all the words that appear and then the alignments of the word that appear to give you like the blue score for this particular pair, and then you average those over all the pairs in your test set. Okay, so looks pretty good. Here's some additional examples. Notice it's getting JP Morgan correct. That's not surprising. Just a proper word or proper name. Just copy it down. However, this isn't like perfect. It still has some issues. So here's an example where there was an issue in alignment. So if you look up here, you have was abandoning, and that gets translated into French as whatever, how do you say that? Abandonner, I don't know. And so that becomes a word that needs to be, this is apparently rare, so this is a word that needs to be copied down, but the copy mechanism didn't grab this whole phrase, and so it just grabs this was, which is translated here. So it sort of misses that, like while it gets the tense right, it misses the fact that this was abandoning and not just was. So still some trickiness there. Needs to be improved, and people who really care about these things start to figure out, in all the cases we're working on, how to make those improvements. And yeah, so anyways, just an example of where it failed. Okay, this next part's really important. Learning about attention. So this is how this is a proposal for how to deal with sentence length, how to translate sentences that are very long. And it's important because when we get to the next lecture, we're going to learn about transformers. And these are mechanisms for doing translations of sentences from one to another. And so, but they have no recurrent units in them at all. They're totally attention-based. So we're going to learn what attention is here, and then we're going to learn how attention is used in the next lecture, and when we learn about transformers. So, anyways, so pay attention to this next part. All right. So, yeah. So again, the sentence length problem is that translation quality degrades when the sentences get longer and longer. So what's the problem here? So let's think about this for a second. So remember what's happening in these recurrent networks. So in this encoder, you input the words in your sentence one at a time, and those get kind of transformed into these vectors. They get embedded and transformed. And the deeper you go, like the more abstract that representation is of this word. And then when you input the next word, not only is there the representation of this word that's being passed through into these units, but also that's being aggregated with the representation that occurred earlier here, that's being passed from this earlier stage of the network. And then those come together and are aggregated. And if you can think back to like the LSTM, you have these forgetting gates and these gate gates and other output gates and things like that. So there's all these ways of kind of like deciding how that happens. But regardless, what you get coming like in this error right here is some combination of the representation of am plus the representation of the entire sentence before it. And similarly, in this next layer up, some representation of am passed through one nonlinear transformation, and then the rest of the sentence at that point in this layer of the network. And this keeps happening until you get to your final stage of the output or of the encoder. Again, the representation for student is being aggregated with the representation of this sentence so far that's here, that's being passed in this arrow. And so that by the time you're done here, what's coming out of this arrow at each layer is just a single vector that's supposed to kind of capture the entire sentence. And the trouble is that this is probably a very hard thing to do. To capture like the meaning of the sentence or like the semantics of the sentence in a single fixed dimensional vector. It's not like, I don't know if that's like a priori obvious, but that's like a tricky thing. Apparently people tell funny jokes about this and laugh at it. I don't know. This is supposed to be somebody who regularly says things like this, but I don't know. So it's just laughing, people who've been doing this kind of work for a long time saying like, how can you expect to jam all the meaning of a sentence into a single vector? Okay, so great. So what? How do we deal with that? So the idea how to deal with that is to not just rely on the representation of the sentence coming out of this stage of the encoder, just that single vector at every layer, but to use all the representations throughout the entire encoder at each stage of the prediction. So, instead of it just being this kind of single stage aggregation, at every time we move forward here, we're going to aggregate all of the vectors that have appeared so far in our encoder. But we're going to do that differently for each step of the decoding. And doing, yeah, so differently, what does that mean? That's what we're going to go through. But we're basically, what this boils down to is we're basically going to take different linear combinations of the vector that appear, in this layer. So we're going to take some linear combination of these as the input to here, and that will be different from the linear combination that's chosen to go into the next stage and so forth with the decoder. So we're using all the information from the encoder this time, and then this operation of like choosing how the linear combination happens, basically the coefficients that you use in this linear combination for each of these vectors, that's known as attention. So those coefficients sort of, just choose which of these vectors you're going to be paying attention to. And so the question is, like, how do we get those coefficients? Well, of course, we learn those as part of the full machine learning process, the full training process. So, so we'll just jump the gun here and say that, so here's these blue scores again. Again, here's some measure of, okay, so here's sentence length in terms of number of words. And you can see that with models that don't have attention, that you see that as the sentence length goes up, you see some kind of climate improvement, but then rapidly as the sentence length gets long, that ability drops off dramatically. However, with attention, you don't see the same drop off. So, how does this work?
A little side question.
Yeah.
Why would short sentences be hard to translate?
Because you don't have as much context to help you translate, right? So, yeah. All right. So how does this work? So, yeah, so the question, so like what we're going to do is kind of how do we build up the representation that should go in that question mark vector there. So what we do is we take this this output here. So this is the vector. Like the output of this is the vector that would normally just be passed here without being changed. And instead, what we do is we take this and we compare it to all of these all the outputs from these units in the encoder. And we have some sort of score for measuring the similarity between the vector coming out of here and the vector coming out of each one of these units. So like, just arbitrarily, there's some score of 3, some similarity of 3. However you do it, doesn't really matter. You just got to pick one way and stick with it. Well, it does matter, but like, as long as you stick with it, you're going to get something consistent. So let's say that that had some similarity of 3. This one had some similarity of 5. Then this one has lower, so 1 and of 1. Okay? So we just compute these scores. So you can think of this as like cosine similarity. I mean, you wouldn't get 1s and 3s and 5s, but like something about like the angle between these vectors, or the Euclidean distance between them, or any other way of computing some sort of similarity. You want to have some measure of saying how much does this like original output look like all the outputs in the encoder. Okay? And once we have that, then we divide by the sum of those so that we have some convex combination of words. So this is kind of like applying softmax, right? We took these numbers, now we converted into probability distribution. So now these are all positive and they sum to 1. Okay? And so these are now our attention coefficients. And now once we have that, we use those to create a linear combination that ends up being a convex combination because of creating a probability distribution out of these. And we create a new vector out of these vectors with those coefficients in the linear combination. So we have this new vector called the context vector, CT, and that is what actually gets input and sent to be used in the next hidden state. So instead of it being this output, it's actually this complex combination of these things that's sent over here. Now this is going to have its own output, and the same process will start all over again, and then that will be sent over. So you follow all the lines in this computational graph, you have a nice feed forward network, and you can train this end to end. Right. Oh, right. And once you've got this hidden state, then you can use that to predict the next word. Right. So we apply softmax to this, and you get your probability distribution over your vocabulary. Choose your word. Okay, does that make sense? So it's pretty straightforward, but it's really, really important. It's taking basically all the information that we have and using it in some way. Questions about that? Yeah.
Sorry, could you repeat what's going on with the dotted line?
Yeah, remember that the dotted line there. So what that's trying to represent is we got these coefficients, these attention scores, by comparing the vector that's here, the output vector from here, with the output vector from each one of these units here. So we calculated a score. So the only role that this played, the role that this played in the state that was passed to this next unit was just in choosing or in calculating these coefficients that were part of the linear combination to give us this vector here, which is actually the one that's passed forward here. And actually, I should correct myself. I've been saying it as if this one can't be passed forward. This can be passed forward too. They both can be passed forward. There's nothing stopping you from doing that. You could combine these, like this output vector with this one in any way you wanted to, and you get some, or you just not get this wrong. But the important thing is that vector is used to create those scores, and those scores are used to choose the coefficients in the linear combination of the outputs from the encoder. So, like when we get together next time and look at transformers, like a vector like this is we think of as the query vector, and these are all let's see, what's the word for these? Yeah, it's a key. I was going to say key, but something seems wrong about that. But anyways, these are all this is like these are like, you think of this as being like a dictionary, and so these are all the keys for like looking up what's in the dictionary there, and then creating this combination to get the final value. So again, like I don't think any of you should like look at this and be like, oh yeah, that totally is going to make everything work. All it is like an attempt to have a to allow all of the information that's in the encoder to play a role in the choosing of the next symbol that's more than just the aggregation that's happened through all these units to a single vector. We're now using like, a basis for some space that we're in to like choose a vector within that larger dimensional space, or like in that, yeah. So there's a bunch of dimensions happening here, but like in that subset of our vector space in which all these live. So it's allowing you to not just work with that fixed vector, but choose something, learn to choose something that should be beneficial. And then when you use backpropagation here now, all the pressure is forcing us to choose good coefficients here. That would be helpful. And it turns out this really helps. As you saw in that graph from before, the blue score stays high for longer and longer sentences.
So this is like an LSTM, then that first red box is going to contain information from the previous, but it's basically,
yeah,
I don't know, it's kind of like more compressed I guess you could say, so it carries the whole meaning.
Yep.
Of all of those words.
Into a single vector.
So we get more information by considering the previous vectors as well.
Yep, that's right. So it's so maybe what you're saying is like in some sense, all the information that's here was used to create the output of this. But it's being compressed every time it goes through one of these units. To a single vector. And so this is just saying like, hey, this information is still around. Let's just go use it again. But it's not just used willy-nilly. Like you do use this vector coming out of this unit as like a way of saying like, hey. So remember, we're calculating similarity scores here. So it is saying something like, hey, these outputs that are similar to this must have somehow like played some like important role in creating this. So let's go get some part of it and include it all together into a vector that we're going to pass forward.
There is still some length in that context vector,
There's still some what?
some fixed length.
Yeah, it's still a fixed length vector of the same size as this other one. I mean, it's a linear combination, so the assumption, I guess you could change this, but like the assumption is like if these units are all the same with shared weights, then yeah, this is also a fixed vector of the same size as this. But again, like you're creating it out of, in this case, out of four vectors rather than just one, right? So it's like it's giving you a way to say like, hey, I got this basis of 4 vectors. Let's pick a vector that now lives in this space that's going to be helpful in.
If it's too long, you have a problem.
No. So the long you're referring to there isn't in the size of this dimension. It's in the length of the sentence itself. So again, remember what's happening here is like this is allowing you. So like this looks pretty short here, but like let's imagine this was a sentence that had 60 words in it, right? So again, what this is doing is this is allowing you to grab the information from all the way from the beginning of the sentence and have it play a major role if it works out that way in the prediction of this next word. And the point of this mechanism of learning how to do this here is to is to learn those kind of long distance relationships. So if this was, I mean, it's hard to do this without actual sentences, but basically it's like saying like this sentence might have a lot of context in it from like different parts of the sentence, and those can now play a role again in this as we learn to do this. So, and for simplicity, I've been referring to the score as like something simple like distance or cosine. But you can learn this score as well. In fact, that's like in the best attention networks. You actually learn that score as well. Like learn how to actually learn how to produce these numbers here. And this can also just be like layers in the neural network, right? So all this can be learned.
So would this be a safe analogy then to say that the first red rectangle is like kind of like the Cliff Notes version that has been compiled from a bunch of chapters, and then this attention is saying like these are how important these chapters were, so like go back and get that information. And use it.
Yeah. That's a nice anthropomorphic way. But yeah, I think that's great. Yeah, it is. And again, like because it's similarity, it's saying like, look, I look a lot like these other things over here. Let's just grab those and bring this all together and reinforce this if that makes sense. So, okay, cool. Makes sense enough? Attention. Okay, so that's the basics of attention. This sort of score, combine, and feed forward mechanism. And we kind of focused on one kind of attention mechanism. That is like you're allowed to pay attention. You're allowed to create this context vector out of all of the states of the encoder. you can imagine other ways of doing this. There's a paper here where that was explored, in depth. So obviously, like most things, there's like lots of variants on the theme. You know the basics now of this. Okay, questions before we move on? I have another graphic now. Yeah.
I'm still trying to wrap my head around that blue box, like in practice. Is that like
Which blue box?
just like any of those boxes?
Yeah. Okay.
That's a
So this is a recurrent cell, right? So like think LSTM or GRU, right? So there's neural network stuff happening in here, right? And it takes like each one of these takes two inputs, the current input and then like the hidden state from the previous stage, and it does transformations on it. So this is like a piece of network, and it takes two inputs and it gives you an output. So what we are really showing here when we combine these things, like these aren't necessarily vectors. The arrow is the vector. Like the arrow it represents the output going from the it's the output from one unit becoming the input for the next. However, when we come up here, this actually represents a vector, which is the linear combination of the outputs of those. So it's a pretty abusive graphic, I suppose, but it's not harmful to think of each of these as as the output from the unit, and that you're just combining it with. Really, it's there's a whole bunch of neural network stuff happening here, and it happens within each of these cells, and then you just connect all these cells together. So it's got a very different flavor than what we think about like when we're doing convolutional networks, because they're usually it's like there's one place that everything comes in and then everything kind of goes out, like in this really linear direction. But here it's sort of the same thing. You think of each of these as like a layer, but really the layers in this they're really like they're like this. This is the layer of the recurrent neural network. This is like the first and the second, and then you could have a third and so forth. This, the fact that you go this way is just capturing the current, like the way that. So this is like the analogy is like this is like the convolutional filter, where the filter was the way of getting at spatial statistics, like learning spatial relationships. This is the way of learning temporal relationships.
And then one last question: the context vector. I'm just trying to get an idea of the math of whatever the context vector multiplied by the first red box will produce.
Well, it's not multiplied by. This is now like so. This is just another recurrent unit. This is like the input to it now. That's all. Yeah. Yes.
So the red layer address will go on until it predicts the finishing.
Exactly.
Word, yes.
Yep. That's exactly right. Yep. Once this just keep going until it produces that stop symbol, and then you hopefully have a good translation at that point. Good. Yeah, so no attention, bad for length, lots of attention, different kinds of attention, they all do a lot better. That's all that says. Let's see, so what are we showing here? I have no idea. We're translating things correctly. It's funny, like, I don't remember this slide. Is that true? Do Orlando Bloom and Miranda Kerr still love each other? I don't know. I don't know. I'm not sure what's going on here. Like, because these are proper names and these are copied down. So I somehow skipped this when I was preparing. So something good happens here with attention. There are no goods. Okay. So let's check this out. So what comes out of these attention mechanisms that maybe we didn't have before? Well, something that gets learned apparently with these long-term or with these attention mechanisms that maybe wasn't happening as well with the seek models, is that you get these really difficult grammatical shifts from like doubly negated phrases, right? So our source sentence in English has this double negative, not incomplete. So if it's not incomplete, then it must be complete, or sorry, complete, compatible. So it must be compatible. Here's your translation, and that word, what does it show up? Is this neat in view? That doesn't make any sense. I wish I worded German better, but the point is that what our base word here has nicht over there, which is not, but it has this word, which I'm guessing is compatible, but it should be negated. And in our best model here, in our attention-based model, we actually get the nicht over there, and you get the negated part here. So the point is that like this model has more capacity to learn a lot more of the grammar, and that where grammar sort of depends on more of the context of the sentence, of being able to detect these kinds of grammatical nuances. Oh, I have it here. Okay, so that's that. Is everybody feeling super confused about that? Or is everybody just like, that's awesome, I would have thought of that myself if I were working on this? Yeah, no. This is what this guy's job is basically. Like Chris Manning there and Joshua Bengio, like that's what they spend their days doing. Just how can we make this better? Oh, I know. Let's do another linear combination. All right. So the last bit of fun here. So language complexity. So we saw this with the character level translation. All right. So this is starting to get at like really difficult problems in language, like really, like especially when you're going from very different languages with very different kinds of structures. So sometimes sometimes these copying mechanisms aren't sufficient. So this could be the case when, say, you go between different alphabets, right? So Christopher is his name, his proper noun, but when you go to a different language, especially with a different alphabet, like copying Christopher down is just not going to work, right? It's just you're going to need Christopher again, and maybe you can tell what's happened there, but it's not the right translation. And then there are tricky things like when you go between, say, like English and something like German or like a Scandinavian language, something like that, where you tend to take these words and combine them, right? So we had a two-word phrase that stood for something, but it then needs to be translated to like a one-word to a single word in a different language, and then this can just get crazy, right? So this is I have no idea what language this is. It's probably something Scandinavian, something like Finnish or something like that. But in a lot of these languages, like you end up just combining a lot of words, and you have this like this. You think of it as like an open vocabulary. Like you can create words that don't really exist in the dictionary because like the grammar allows you to just sort of combine them. So these would never appear in a full dictionary, but this is still grammatically correct. And then kind of goofy things that you would see a lot of these days, just by there's just kind of silly ways of doing things that provide emphasis and have meaning, but don't adhere directly to like grammatical or syntactic rules of the language. So we'd like to be able to deal with stuff like this in some way to make our machine translation system even better. So I propose a solution for the So what we're going to do is we're going to look at character level. We're going to introduce character level translations when the words become really tricky. So there are previous attempts at this, but here's the one that we're going to deal with. This gave an impressive 11.4, like an improvement of 11.4 in the blue score for really difficult translations like this is English to Czech. Anybody speak Czech in here? Read it? No? Boring. All right. So what we have is we have basically a hybrid network where we have a seek-to-seek model, and this ends up being fairly deep, I guess. So we'll have our typical seek-to-seek model at the word level. However, within each of these networks, if we predict like the unknown symbol, then what we are allowed to do is sort of drop into a much deeper model that actually learns to do the translations of one word to another in the other language. So instead of the vocabulary now being words, it's the alphabet for that language. All right, so still seek to seek, but if we get something that's unknown, so that means that the word is rare. Instead of doing this copy mechanism, we might still need to do this copy mechanism. This can still happen. However, what we want to be able to do is learn to do these translations of one word to the other. So you basically have like kind of two sets of networks interacting whenever an unknown character gets predicted. Does that make sense? So it's like we want to work at the word level, but as soon as like something is rare, then we start working at the character level for those words. And we train this all end to end. Yeah, so this is just commenting on like the fact that you just use really simple embeddings for the alphabet and initializations, and you just try to do your very best here without a whole lot of try not to do a whole lot of like pre and post processing for the character level network. Oops. Okay. Yeah, and so the unknowns in this system, we need them to stick around because so as we are decoding, especially in the test set case, we need these unknowns to stick around again for alignment to say like, okay, what are we going to translate from or from and to? So just kind of keeping track. Anyways, so I don't know Czech very well, but I've been to Czech Republic a couple times and looked at the words there, and it looks very different from English. And this is a really difficult problem. So what this is showing is that in this hybrid system, well, before the hybrid system, this is like state of the art for this problem. So you get a glue score of 18.8. This is at the word level. Single model, so this is an ensemble of various systems, various models, sorry. Single model gets 15.7, ensemble of four models get 18.3. But when we add this, this is character based. So this is like not word level. This is actually doing like translating sentences where you actually just translate each letter to another one, including things like the punctuation and spaces and things like that. It's a 50.9 at this point was slow but promising, but this hybrid system here, this really difficult problem, and then for a single model gets a glue score of 19.6. So combining translation at the word level where that is like, it's easy to work at that level, but then dropping down to this character translation when the words are unknown actually gets you to this better score. This is back in 2015, so lots has happened from since then, and we're going to start going through those things next time we get together. Yeah, and core models, and some will always do better. You already knew that since you're machine learning experts. All right, so this is, So this is how, so this is, back a couple of years ago, this is how, in a couple of years, we went from, here are decent models that actually do machine translation with neural networks in an end-to-end manner in a good way, and over the course of a year or two, adding in a couple of these mechanisms, and then now having state-of-the-art for various pairs of languages translation. And these were the things that were used in things like Google Translate and other like machine translation systems until transformers came along. And now those are the things.
So when doing this stackable translation, can we add like that context from another or space for each character?
Yes, you could do that too. Yeah, you can have it. I think what you're asking is, could you have an attention mechanism at the character? Yeah, absolutely. Yeah. That's a very different. So I don't know off the top of my head like how. So like mechanics of it, you can absolutely do it. I'm not sure how much of a benefit that is, but I can see how that probably is for like these kind of crazy compound words that we saw, because like there's also like really long range relationships there between like the beginning and the end of the sentence, and probably helps a lot. I don't know a lot about that, but yeah, you could definitely do it, and it probably helps in situations like that. Yeah, good. Okay. If you have any questions, you can let me know, but that's it for today. So have a good one. Get your proposals turned in, and I'm excited to read this.
I'll submit our proposal. Do you guys want to do that?
So I'm not totally sure what you're asking, but it sounds like we're going to get pictures for, then you want to like fine tune it for, but then for some reason you're like adding additional layers.
Yeah.
So that usually becomes a problem in fine tuning, because while this is all like fine tuned, it then becomes like random output over here, right? Right. So there's like no signal to grab onto. So then what happens there usually is that not only do these change a lot, but this changes a lot, and like you're losing the goodness.
Yeah, so that's
So you don't want these guys.
It's still created that kind of thing.
So just on. Yeah, so like there's a couple ways to do this. Like basically, you don't usually like add on layers. What you typically do is you take like the final layers in these kind of networks, and then you unfreeze those. So you keep most of the like you're not changing the weights of the train, and you just update the things at the end, because the things at the end should represent like everything inside of this network has learned a lot about language and relationships with language, and you don't want to mess with that. What you want to mess with is like how it takes all those relationships and then makes a slightly different set of decisions for this data set. So what you mean is that it's like
procedure that is
But why do you even want these? I don't understand. You don't even want these. You just don't. No, like if you're just trying to take this pre-train and then fine tune it for like this data set, you don't need additional layers. You just need to fine tune the final layers on that. Right. So that doesn't mean adding layers. That means fine tune. That means changing the final layers in this network.
You're making this only without final layers
to change. Exactly. And so we're going to do transformers revert. Let's talk about this again after we move. Okay. Nice.
We are colleagues. Good.
Okay.
Training mode means more like
more, yeah. But that's why I'm asking, right?
Well, there's one of the like one of the messages that's told is that like every generation is costly, and especially for disabled, right? So like don't forget that that's like 4 weeks to work on this small. No, it's, yeah. No, maxed out credit cards. Yeah, it's so
everything looks cool.
expression.
Maybe I should be this one for and
Yeah.
the regression is what? Oh, you mean like actually evaluates what that expression is? Purely, yeah, I see. Yeah, so you can generate your own evidence.
Yeah, exactly. Easy.
Yeah, that sounds cool. So what a convolutional network works, I would guess no way would have worked. It's like, because like, but like, okay, let's just take something simple. So you.
No, that's
Sorry. X plus 1, like 2 plus 3, right?
Right.
Because you have
Two numbers add together.
Well, okay, maybe something this simple. So what you're asking me to do basically is, so this is something, and now you start passing filter functions, right? So what you're asking me to do is, through its layers, you're trying to build up. Like, okay, so you're probably going to simplify that.
10, 20.
So you're basically asking to build up something that's something like, there's a representation of 2 here, there's a representation of n, add in here, and a representation of 3. Now, it doesn't have to be here, like, it could have already been here, but the trouble is, like, convolution isn't like that. Convolution isn't like semantic in the sense of like, as I do these filters, like it's going to learn something. It's just like, it just keeps like processing the pixel itself, right? So you're just, like, you're getting something over here that maybe says, like, there's a 2 here, there's a, hey, like there's a 2 here, and there's a plus here, and there's a 3 here, this is what you're hoping for, like, and then that sort of comes out in this fully connected layer. But like, and maybe it could learn the fact that like if this is on the left, this is on the right, or I mean, we can't. It's hard to anticipate what neural networks actually learn. But like, the convolution operation isn't like really great for this. Like the recurrent operation is really excellent for this because you're learning. You have representation of this, representation of this, representation of this. And then end, right? And end here is evaluate, and you have a single output, which is regression, which isn't like we've been doing like when you classification regression, but you can totally do this. Just change the head on this instead of being soft regression, and your loss be what it should be. So that has a better chance of working. However, there's nothing like, it seems like a pretty fun thing to do, just to try this and just see what happens. But I'm guessing this would like totally flop. So if it's really flopping, you should especially for simple things, you have a very simple vocabulary. So you might want to limit this to like basic arithmetic. Adding, subtracting, and then
I was like, let's go integrals over polynomials.
Well, that would be awesome. That would be really awesome, right? You're gonna have to see a lot of integrals over polynomials, right? However, like you could, there's a cool idea here because like if this can learn to do basic monomials, and then the polynomial is the sum of those, like it might be able to learn to do that. Like you try to see if you can get it to learn these, and then you just have sums of those, and then just see how it goes. Like that you just don't start off with it being really hard. Start off with something very simple that like makes sense. Like single digit numbers. Of course, like this is going to have to regress.
Is that like you need more than single digit numbers because you only have
20 combination,
Under combination, single digit, so like,
Yeah.
that's like 6-digit numbers,
Yeah.
which, I don't know, I think, so I think, kind of what you're saying is,
Yeah.
you can do that as a project, you can give it.
I think it's super cool. I think you guys should do something along those lines for sure. Yeah.
Because I think even like, potentially you could learn other ways, like, to try to estimate these.
Like
Because, like,
proof theorem.
Like when I'm thinking of this, like when I think you're like adding 6 by 6, it might even be like, it's latex, it's like black and white, like this much, okay, it's like, you could add like a simple version, you add like 1, 2, 3, 4 plus 6. This has more black space than this, which means that this is gonna be like a higher number. So like, might end up learning things that are maybe like a little bit not as intuitive, or not like you would try to estimate.
Right. So the other thing you could do too is like, you could actually detect, so like if these are handwritten, which I don't know if you're reading lots actually. But you could still have, even if it wasn't handwritten, you have to detect all of the individual numbers, like you could use the, kind of like the faster CNN stuff to get all these, so you have all these others, but you want to have some sort of ordering for them, so the key here would be like, learn the objects and learn the orders. Like, this is where your supervised data becomes really, like, important. So like, if this is what you need to do, learn the ordering, you have to somehow give it like, here's the mask for the number, and here's the ordering for these numbers. And so like, you have to learn both of those things. But so that requires more labeling, but like, that's pretty cool. Don't do something super hard. Do something super easy, but still kind of interesting, and have a lot of fun and try to make it work. And I think that's awesome.
We were basically saying like, should we do this project or not? Sound like, go ahead.
No, just don't go crazy. Don't go crazy first. Do try this first, right? Because I think that's what we're saying. Because I know that there's not much data, but that's okay. Like, maybe this is just like a very simple network that learns to do this, right? Your RNN on like a very simple RNN on like a single cell, or probably can learn to do like this regression really, really easy, because like the data is so straightforward. But I don't know. You have to go find out.
So the other difficult part is that this census is so weird, there's not really papers out there to do something like this.
Yeah,
Like
right.
a farm.
Yeah.
So,
But I mean, so what?
And
So
I mean,
so there.
so
Well,
you've done everything.
so it doesn't have to be exactly the same thing. So like, what are the things you have to solve for? So, if you do this, you need to solve.
added up correctly.
It's not just detecting the objects in here, but like something about like, some property that this whole thing represents, right?
Okay.
So, you want to look for a paper that's like analogous to that idea. So,
Okay.
like a lot of what we want to do is we want to say like, there's two, we want to detect two objects. What you want to do is like, there's this whole thing and it evaluates it. So I can't think of something on top of my head that you want to look for.
Some sort of metric, like someone that's using a convolutional network to
like
spit out a metric.
Yeah, to not spit out like the thing that's there, but like something related to it. So, like, the thing that just came to mind is this is not great, but like, it's a classification problem, although you're going to use regression.
We'll have an infinite number of classifications.
Well, you don't have to have anything, like if these are single digit, then you know how many.
That's true.
You just kind of look for stuff like that. There's all kinds of stuff, and then just find stuff. It'll job. It's just the process of finding different papers will like. Well, it's trigger thing. We'll see other things. It might shape your project.
I just said like,
It's just
researching.
Yeah, and if you literally can't find anything, like, I guess I'll leave that if you break the old college try, but throw some things that are not that close.
Right. Yeah, we have some things. Right. The way you do it in your series project is just
Rather than
take this image, find these characters,
I don't think
string
you
these
need
characters
to
together.
Well, so there's definitely so one paper that you should definitely, I've seen this before. Is it a paper?
Has it changed?
Might just be an example, but there is definitely like character level. So there's RNNs trained on LaTeX, the character. So like not in the image, but like the actual LaTeX code. So it's trained like it trains the character RNN to just start generating this, and so you can just generate like arbitrary LaTeX. It's not particularly like you have to do some tricks to make sure that it's like actually like syntactically correct LaTeX that will actually compile. And so like if you go look at these things like find the papers or like stuff, then like this is good stuff for you to learn about. I know you think about characters here, but you could go down to the LaTeX level and work it. I don't know. So there's stuff.
Exactly.
Okay, have fun. Next question.
Well,
Is your Carlos?
the solution though have the same number of parameters.
We need a lot more and those require so many GPUs. In fact, Alpha 0, let's see. One of the alphas used TPUs.
Like 4 TPUs.
Right. Exactly. So that's really, really expensive.
Okay.
That's a really cool project, but you just don't have the compute available to you.
Okay, good to know.
Like you have, amongst the three of you, will have $150 on GCP. But that's going to blow through that in a second. So.
Good to know.
Yeah.
All right.
But if you're interested in gameplay and things like that, there's far simpler things like that are available to you. Like OpenAI Gym, where you can train on some like simpler Atari games. That would be a good project because it would just be like recreating what other people have done. But like somehow you could do this with a game you haven't done or whatever. That would be cool.
Okay. So what was that called?
OpenAI. So Open.ai. Okay. So this is a research. It's not a company. It's like a research. Like organization. It's funded, by private money, but it's all like kind of company. It's like Elon Musk has got money in this.
Okay.
And they employ hundreds of researchers who are using all kinds of things. So they have a project called Gym. You can just go look at OpenAI Gym, and this is basically
if you're like grading
a
that,
whole bunch of code and like a whole framework for training reinforcement learning models on like Atari type games.
Okay.
And they have they have a whole they make it really easy for you to learn to do this on existing games that they have in the gym.
Okay.
And then from that you can learn to do something else. Like I said, it wouldn't be a good project just to do one of the existing projects, but have to be something else, which might be kind of tricky because it's required to get the frames of the game as data. But I don't know, you can just search around and see. You can learn to play much simpler games without, with reinforcement learning, I don't know, tic-tac-toe and stuff like that. You know, see what you can do.
Okay.
But
cool.
I don't know. So hopefully that didn't dash all your videos, but
no, that's fine.
Yeah, it would be really bad to kind of get going in that direction and realize that.
Yeah.
An hour on TPU costs, $8 or something like that.
Oh, let me save things.
Yeah.
Okay. Good to know. All right.
Okay. Yeah. How's it going?
Good. So we're doing, my team and I were in the wireless comms and stuff.
Okay.
I want to do some noise, distribution parameters or something. Complex.
Like how to denoise a signal?
Yeah, so we did.
I mean, that's a really awesome project. If you have paired data, if you have like a PCI signal and you have the denoise version of it, that's a really cool project. You can take
So we can generate that.
Yes, you can take a signal that's not noisy or has like little noise in it, and then you can add more to it, right? And so you can create your pairs like that, like learn so your supervision is the input is this noisy sequence, and the output is this clean sequence. It's a straightforward like seek to seek problem.
So you're seeing some stuff like mixture density networks,
You ever heard of those?
So,
Yeah.
I mean,
Right now, it's the newest thing.
I don't know, yeah, I know very little about that, so let's see.
And we talked about
This is still running, Alex, should we turn it off?
Oh, right, thanks.
Let's see.